Okay, Assalamualaikum warahmatullahi wabarakatuh. So today I will share with you content course regarding static and dynamic. Okay, fundamental regarding static and dynamic. So this course maybe will help you in for fundamental parts for aerospace structure or aerospace composite. Okay, so what we are going to see in this refresher course, okay, we are going to look at the force, moment, resultant equilibrium. Maybe this one is a refresher contents for you, free body diagram, support reactions, distributed force, etc., Newton's law, etc. Okay. So at the end of this chapter, we should be able to decompose and combine force and moments in Cartesian space, solve static equilibrium problems, understand the concept of moment, forces and moments of the motion and deformation of a body. Okay, let's first take a look on the Newton's law of motion. So I think you already know there is this actually three Newton's law and plus another one, Newton's law of gravitation. Okay, so what does this Newton's first law mention? So the first law, if the resultant force on a particle is zero, the particle will remain at rest or continue to move in a straight line at constant speed. So if there is no force exerts on the particle, on the material, so the particle will remain at rest. Okay, so a particle will remain at rest unless there is a force acting on the particle. So that is the first law. Second law, a particle of mass will have an acceleration proportional to a non-zero resultant applied force. So this one, what does it mean? This is actually the famous relation that we usually use, which is the sum of the force. Okay, sum of the force. Yeah. Okay. Sum of the force. Okay, sum of the force equals to MA. Okay, sum of the force equals to MA. So this is what it means by the Newton's second law. A particle of mass M will have an acceleration A proportional to a non-zero resultant applied force. So F equals to MA. So that is the relation for Newton's second law. The third law, the force of action and reaction between two particles have the same magnitude and line of action with opposite sense. So what does this third law means? That if you have an action, okay, if you act, if you put a force to a particle between two particles, okay, so there will exist another force with the same magnitude but at opposite direction. Okay, for example, if we have these two particles A and B, okay, A and B, if there is a force reacting, okay, so if there is a force reacting on force A in this direction, for example, with magnitude 10 Newton, there exists another force reacting on the opposite direction. Okay, opposite direction means that, for example, here negative 10 Newton. Okay, if we have 10, because we have the third law mentioned that we need to have the same magnitude. So if we have 10 Newton from a left, okay, so it should be, there is a reaction force on your right, okay, with different opposite sense, opposite direction. So opposite direction, that's why it has positive, negative. So this is what we, with this Newton law, this is what we apply, do for propulsion of aircraft engine. Okay, so aircraft engine, they need in order for an aircraft to propel, okay, so we need to have a reaction and action on the, for example, here this is the engine of the aircraft. Okay, so we must the aircraft actually, it obeys, it follows the Newton's third law rule. Okay, so that's why it we will have thrust force existing on the aircraft engine, and the opposite direction will be drag. Okay, the drag force. So due to this, okay, due to the drag force, then due to the drag force exercised on the engine, aircraft engine, then we will produce thrust force in order for the aircraft to propel. So aircraft engine actually follows the Newton's third law. So Newton's third law is applied to the engine. So that is an example. Application of Newton's third law. Otherwise, we have Newton's law of gravitation. Okay, two particles are attracted with equal and opposite force. So kind of like the same as the third law. Okay, so but this is applied to an object which has a gravitational force access on the object or mass. Okay, next. Okay, so unit vector. So this one we have seen in how to use vector. This one we have seen in engineering maths course, right? Okay, I think the first chapter in maths. So by now you already know the definition of vector. So we have, if we have three components of vector, so we of the vector. So we have in three direction. Okay, vx, vy, vz. Okay. So if we have a force, so a force is a vector because it has direction. Okay, so a force with a magnitude of 600 Newton. Okay, express F as a vector in terms of the unit vectors I and J. Identify the X and Y scalar components of F. Okay, so if you have a force of 600 Newton, how we are going to decompose the force in X and Y direction? So each force, okay, for example, here we have a 2D, two axis. So the force can be decomposed into different directions. So this one we will call it as Fx, and this one is Fy. Okay, the direction of Y and X. So by knowing the angle, okay, the angle of the direction of the force, so we can calculate, okay, we can compute the value of Fx and Fy. So normally Fx is F, okay, 600 Newton cosinus 40 degree. And Fy is F sinus 40 degree. Okay, this is, we use the theorem of Pythagoras. Okay, Pythagoras theorem. Okay, so we have if this is the force F, so the angle here 40 degree. Okay, so in order to get this will be Fx and this will be Fy. So the direction here, okay, the direction here, in order to get the Fx, so we need to use cosinus, because cosinus theta is Fx, okay, the one beside the angle, over F. Okay. Okay. Okay, next. Okay, next we have okay, the first assignment. Okay, this one. Okay, so we have to define carefully. Okay, because Y is in the downward direction, so Fy will become in negative direction. Okay. Okay, so what if we have a static resultant force? Okay, if you have static resultant force, okay, so the force can be decomposed into three different directions. So R, for example, here R is the resultant of the three force P, Q, and S. Okay, so for each we can calculate R. Okay, we can calculate R by knowing all the forces of the other all the other three forces, which is P, Q, and S. So here, for example, okay, we know P, Q, and S, and with their own direction, X and Y. So PY, PX, QX, QY, SY, SX, etc. So by knowing all the direction, for example, the components of PX, QS, CS, so the sum of those component of the forces PX, QS, SS will become Rx, since the vector R is the sum of the force PQS. So the component of the force PX, QS, SS is also the sum of the component of X for R force. Okay. Okay, I repeat. Okay, since R is the sum of the force PQS, so the component of each of this force PX, QS, and SS, and also PY, QY, and SY are also the sum of this force component force are also will become the component of RY or RX. Okay. So and then to find the resultant force, to find the resultant force, we get magnitude and direction of R. Okay, so the magnitude and directions, it's like the theorem again. By using the Pythagoras theorem, we can get R by Rs square plus Ry square. So this is the normal Pythagoras theorem. Okay, so this is an example. Okay, you can take a look at this example later on. Okay, how we decompose, how we calculate the force R, okay, in this example. Okay, so R is like this one. Okay, so we are going to calculate, okay, the sum of the force R. We are going to calculate what is the magnitude of R and the angle. Okay, so since R is the sum of the force of 500 and 780 Newton, this one and this one, okay, and also this one, sorry, 725. So this is the PQX just now. So we can calculate the resultant force, which is R, okay, by knowing the magnitude of PQS and the component of each of the PX, QS, etc. Okay, just like the formula given here. So if you use that to apply, then you can calculate R, the resultant force, the magnitude, and the angle of R. Okay, so you get Rs, you get Ry, and the sum of Rs and Ry square root using theorem Pythagoras, you get the sum the force R 225.9 Newton. Okay. Okay, next is moment. So what is moment? Moment of a force about a point is the measure of the tendency of the force to cause rotation about the point. Okay, so moment is actually when a force acting on particles, or a force acting on the material, and the force cause a rotation, a movement. Okay, due to the force, it causes movement to the material. Okay, so this movement, movement is called moment of the force. Okay, the moment is the movement due to the force. Okay, so how are we going to calculate the moment? So the moment is force, the force that we acting on the material. R is the radius. Okay, the radius of the rotation it causes, okay, to rotate the material, and sinus alpha, the angle of the rotation here. Okay, or otherwise we can also direct calculate it F and D, the direction to the tangent of the perpendicular direction to the moment, to the material. Okay, so this is how we calculate moment. Okay, so for example here, if we have attachment, okay, a television attached to the shaft, to the wall. Okay, a television is attached to the wall. So normally we will locate the television as close as possible to the wall, right? We do not locate the television too far from the wall like this, because if we do like this, okay, then it will cause moment. Okay, there is a the moment of location. This one is higher, the moment of this one. So when the moment is higher means that it will rotate. So if it rotates, then the television will drop. Okay, so that's why in this case, okay, we know that if we put the television too far from the wall, it will cause moment. Okay, moment of the force will be higher because the television could rotate, could movement, could move, so it will fail. So in this situation, we will usually place the television very close to the wall so that the moment will be very small or zero. Okay. So example here, what is the moment of the 40 kilonewton force about point A? Okay. So if you calculate this one, we can just calculate F. So the in here we use sinus just now. Okay, M to calculate moment. M. So M is F R sinus alpha or theta. Okay. Okay. So F is 40 kilonewton. Okay. Wait, 40 kilonewton. Sorry. Okay, momentum of moment is 120 kilonewton. The direction of the okay. I forgot how did I did this before this. Okay, F. Okay, so F is 40 kilonewton. Okay, and R is 6 meter. Okay, so sinus alpha, sinus 30 degree is 0.5. Okay, so that's why you get 130 kilonewton. Okay. So next, static equilibrium. Okay, so static equilibrium if a body is at rest or moving at constant velocity. Okay, if we have these two conditions, at rest and moving at constant velocity, so the sum of the force and the sum of the moment will become zero if the body is at rest or moving at a constant velocity. Okay, so if you have these two conditions, we will have the condition of equilibrium. So what are the conditions for equilibrium? The condition for equilibrium is the sum of the force equals to zero and the sum of the moment equals to zero. Okay. 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 So free body diagram. Okay. Free body diagram. In order to fully understand the effects of force on a body, we need to identify all forces acting on the body. Okay. Generally, if a support prevents or resists the translation of a body, then a reaction force is developed. Likewise, if rotation is prevented or resisted, or reaction moment is exerted on the body. Okay, so what free body diagram? Okay, we use free body diagram. Free body diagram is a tool very useful for identifying all force and moments. Okay, for example, like this. Okay, these are the example of for support reaction type of contact. Okay, for example here, give you example here, the first one. Okay, if you have a flexible cable, belt, chain, or rope. Okay, so the so if the cable has a force, okay, exerting on the cable, for example, force force T here. Okay, so we will kind of like assimilate the force, the tension force here, okay, acting as T, okay, and the force will be in this direction due to the tension, okay, tension force due to caused by the rope. Okay, so force exerted by a flexible cable is always a tension away from the body in the direction of the cable. Okay, so the tension is the force that acting on the cable. Okay, so second example, if you have a smooth surface like this, even though it's a smooth surface, but actually there is a force, okay, at the contact. There is a force exerting on the normal direction, okay, normal direction to the surface of the contact. Okay, if you have a material, okay, on the smooth surface like this, okay, so even though the material do not actually not moving, but there is always a normal force that we call as compressive force acting on the material, on the particles, so that the particle can be placed at the surface. Okay, it will not move. Okay. Okay, and the rest, rough surface, roller support. So those are the example of the reaction. Okay, so action force caused on a body. Okay, even though the body is fixed, okay, it doesn't move, but there is always force, normal force, or tension force, etc., acting on the particles, on the materials. Okay, so for example here, pin support, roller support. So those are the support reaction acting on the material. Okay, spring action. Okay, spring, even the spring. Okay, spring or rubber band, something like that. Okay, so the spring. Okay, spring force is tensile if spring is stretched, and compressive if compressed. Okay, so the spring can be compressed or stretched. Okay, so for a linearly elastic spring, the stiffness K, okay, the stiffness K is the force required to deform the spring a unit distance. Okay, so if you use a spring, then a force will apply to the spring. Okay. Okay, so the force will exert on the material. So this is what we call as Hooke's law, F equals to Kx. Okay, Hooke's law. Okay, so Hooke's law, you can use this law to a spring like this. Okay, an elastic spring. Okay, so it is linear. Linear means that, okay, is directly proportional to the force. So if we increase the force acting on the spring, the force of the spring, if you increase the force, then the distance x that we stretch the spring will increase. Okay, if you increase F, then X will also increase. If you increase S, then force will also increase. Sorry, the opposite way. If you increase X, then force will increase. Okay, so that is what is called linearly. Okay, so this is the elastic force, okay, for spring action. And these are the example of free body diagram. Okay, so this free body diagram can be applied in many construction materials. Okay, so in a beam, etc. Okay. Okay, example. Okay, this is example of the problem. You can take a look at the example here. Determine the magnitude P of the tension in the supporting cable and the magnitude of the force on the pin A for the crane below. Okay, so look at this example, how the force, the sum of the force is calculated for this example of free body diagram. Okay. Okay, so otherwise there exists also force due to the position or depth, kedalaman. This is due to the pressure of the water. Okay, so the force acting on this situation, how to calculate the force? Okay, but the force is due to the water pressure. Okay, So we will take into consideration the depth, rho, h, the height. Okay, so this is h, the gravitational acceleration, and the density of the fluid, which is here water, the density of the water. So some loads is a function of position or depth, such as water pressure. For example, the load is the load is has some pressure acting on the load, okay, on the material. This is the load, okay. So how we are going to calculate the force acting on the load? We have to take into consideration the pressure that the water or etc. Cause to the load. Okay. Okay. Another one is what we call as a centroid. Okay, centroid or center. Okay, centroid of area. Okay. In a structure, we also have to take into consideration this centroid. Okay, so how we are going to calculate a centroid of an area? For example, here we have area like this, an area like this. So to calculate the centroid of the area, this surface, okay. So the centroid, we calculate the centroid for x, y, and z, the position of x, y, and z. Okay, so it is an integral of this integral of x over the surface A, or the integral of y or z over the surface A. So that is how we calculate the centroid in a Cartesian space s, y, z. Okay, or sometimes instead of doing integral, okay, we can also sorry, calculate like this: the sum of the area multiply with the location x or y. Okay, we look at the example. Centroid of some common. So this is to show you the point of centroid. Where is the location of the centroid for each of this common area. So if we have a cone, a quarter of a sphere, a circular, etc. So to find the centroid is C here. Okay, this is the centroid. To find the location of the centroid, okay, and for this area, for this segment of area, we can use the calculation, the formula just now, but the location will be like this. Okay, okay, around here. So we need to know the centroid of this area, the center point of this area. Okay, so we know that if we know the center point, we know where is the gravitational force will act on this area. Okay, so that's why it's important to know the centroid of the area, semi-parabolic area, trapezoidal area, etc. Okay, so these are all the examples. We have all the areas formula for this. Okay, so sometimes, okay, if you want to use the formula of the summative here, if you want to calculate the centroid by using the sum of the area and the location like this, okay, you can decompose, okay, divide the area into several base areas. So for example, like this, we have this like this material like this, okay, the concrete like this, the structure. So you can, in order to calculate the centroid for the centroid of this load, this material, we can divide it into separate area for us, easier to calculate the centroid. So we divide it into a triangle like this, a square like this, and also a triangle like this. Okay. Okay. Determine the centroid of the angle section shown in the right figure. Sorry. Okay. So this is an example. If we have the material in L shape like this, okay, we can divide, okay, to calculate the centroid, we can separate the material into two different surface. One is like this, and then the one is this one, and then we calculate for the centroid of each point. X and Y. Okay. Okay, this is an example also. You can try to do it. Okay. Next is area moment of inertia. Okay, area moment of inertia. Okay, so as also known as the second moments of area. Okay, you know inertia. Okay, inertia. So we have also moment of inertia, which is calculated in area unit, meter square, meter power of 4. Okay, so that's why it is called an area. So the equation to calculate the area at the moment of inertia is ISS and IYY like this. Okay, so this is the integral of y square and integral of x square. Okay, if you want to find the moment of inertia in the x direction, we do the integral for our y square, and if you want to find the initial moment of inertia for y direction, we do the integral of x square. Okay, you see example like this one. Okay, determine the moment of inertia of a rectangle about n axis through the center and parallel to the box. Okay, so okay, we calculate first the IXX here. Okay, so the formula is integral of y square. Okay, so IXX. Okay, so y square, we separate the dA here into b dy. Okay, since the function is a function of y, so we leave it the dy here, but b here in the y direction, we know the length. Okay, the length of b here. Okay, but the y will be the small particle y, so we will write it as dy. Okay, so y b dy. Okay, from negative. So we assume that this is a 0. Okay, here is 0. So negative 2 point d over 2 to d over 2. Okay, this one. Okay, so integrate, do the integration, calculate. So we have for this rectangle box. Okay, for this rectangle, the moment of inertia in the x direction is bd cube over 12. Okay, so and then okay, what if, okay, just now is a rectangle, so it's quite direct. So what if we have a particle that's really don't have a specific shape, okay, like this. Okay, so to calculate the moment of inertia of this axis of the centroid, okay, we will use this equation. Okay, calculate the moment of inertia of the centroid plus the sum, okay, A plus the area y square of the segment. Okay. For example, this one, this is longer, but you can take a look at this. Okay, so for example, this one, so we have this concrete like this, structure like this. So we can separate the structure into 3 different surface 1, surface 2, area 3. Okay, so we calculate the moment of inertia of these 3 separate surface 1, 2, and 3. Okay, we calculate the moment of the area moment of inertia for this set 3, and then we sum up, total it up, and we get the moment of inertia of the whole structure. Okay, so this one. The area 1 and 3 is actually the same, because even though the sketching looks different, but the size is actually, the dimension is the same. So that's why ISS1 is the same as ISS3, so become 2 ISS1. Okay, so here so for example, for the surface 2 here, for this surface 2 here, okay, the equation just now, okay. Okay, so for example, the surface number 2, okay, this one, this calculation. So since it is a rectangle, okay, so we can use the formula of the moment of inertia for a rectangle that we have defined just now. Okay, so which is BD cube. Okay, the x the apa tu panjang dia tu B this one B and D. Okay, BD cube over 12. Okay, so we use this one. So 1 over 12. Okay, for rectangle, 1 over 12. Okay, so the B is, okay, B here, B is 3 over 8. So we write 3 over 8. And the D is this one, 3 plus 3 inch. 3 plus 3 inch, power of 3. Okay, so that is the moment of inertia for surface 2. And we do the same for surface 1. Okay. For the surface one is longer because we have to minus a bit, but it's the same formula. You use BD cube over 12. Okay, for a rectangle because we already defined the formula. So the same as for IYY. Okay, IYY also the same, BD square, BD cube over 12. Okay. Okay. So area moment of inertia. So there is other example. Okay, so these are the formulas of the area of moment of inertia that has already been defined. If you have a rectangle, triangle, sphere, okay, so the moment of inertia, the formula is already been defined. Okay, it's already been defined. So we can just apply it, okay, and use to calculate our moment of inertia. Okay. Force and moment relation. Okay, now we have finished the static part. Okay, so static part is a bit longer. Okay, so hope that we understand how to calculate force, moment of inertia. Okay, now dynamics. Okay, dynamics is just a small part. Okay, dynamics. Okay, dynamics. Okay, first kinetics first. Relationship of force and motion. Force and moments, of course, moment of the force can cause motion of an object. So if we put force to an object or a moment to an object, it will cause the object to move. Okay, if the force is enough. Okay. Okay, so example of aircraft, like I said just now, aircraft also follows the Newton's third law. So once there is an action on the force, drag force, so there is a reaction opposite direction of the force, which is the thrust. Okay, so by understand this, okay, we can use all these principles, law, force and acceleration by using Newton's second law. Velocities and displacement to calculate velocity and displacement by using work and energy concept, and velocities and time by using the impulse momentum formula. Okay, let's take a look at this. Okay, Newton's second law. So this is one of the most important second law. It's Newton's second law, which is the sum of the force equals to MA. The sum of the force equals to MA. Newton's second law, right? Okay, so Newton's second law can be used to calculate the sum of the force acting on a particle. Okay, acting on a particle, especially when the particle is on movement. So we can calculate the thrust force, the weight, etc. Okay, so effect of force. Okay, let's look back at the force acting, the elastic force acting on the spring. Okay, so the spring has a stiffness or spring constant K. So if we stretch, okay, deform the spring, okay, to a certain position, then the spring will create a force that we call as elastic force, which is F. At the same time, okay, we can observe the change of position, velocity, acceleration. Okay, if we stretch the spring. But at the same time, the movement, the change that we cannot see, cannot be observed, is the storage of force as energy, which is elastic potential energy, gravitational potential energy, and kinetic energy. Okay, what does it mean here? Static. Okay, in static, we can observe the effects of the change, okay, to the material in static. Okay, statik biasanya kita boleh nampak dia punya kesan macam impak kepada perubahan tu. Tapi dynamic, benda yang kita tak nampak. Bukanlah tak nampak, dia macam non-observable lah, kan? Cannot be directly observed, but it exists. Okay, it exists due to the movement. Okay, for example here spring. When we stretch the spring, okay, the spring will change position, right? The material will change position from A0 to A1, A2, etc. Change position, we create a velocity, acceleration, etc. But the thing that we doesn't see, when we stretch the spring, it actually create potential energy storage that is stored within the material A. Due to the force that we apply on the material A, it creates potential energy. Okay, this thing we cannot see, but it exists. Okay, that's why we need to understand the dynamic of the force. Okay, dynamic ni benda yang kita tak nampak sangat, tapi benda tu exist. So kita kena take into consideration juga benda tu. Soalnya energy lah, kan? Energy sebab dia store dalam tu potential energy macam tu. Okay, so ada example, okay, tak apa. Okay, the same thing as movement of the simple harmonic motion involves dynamic balance of force and energy. Like this. Okay, so there is a force weight, for example, acting on the material, on the particle here in this direction. Okay. And then impulse. Okay, impulse. Okay, so from this force we can calculate impulse of a force. Okay, so impulse of a force is the force multiplied with time. Okay, so the final momentum of the particle can be obtained by adding vectorially its initial momentum and the impulse of the force during the time interval. Okay, in order to calculate the momentum, okay, the momentum of a particle, we need to calculate, okay, we need to take into consideration the impulse of the force. So the moment of a particle, actually, the moment of the particles is actually, okay, the moment of the particle is actually the momentum, initial momentum of the force plus the impulse. Impulse is force time multiplied with the time. Okay, impact tests are often analyzed by using momentum methods. Okay, to calculate the impact of a crash or something. Okay, so we use the momentum methods like this one. Okay, momentum method to calculate the impact. Okay, impact used in impact test. Okay, so finally, okay, the learning outcomes of this short refreshing course is to decompose and combine force and moments into Cartesian space. Okay, so by now you understand how to combine or to decompose force and moments, like just now Fx, Fy, the resultants, force, moment, etc. Okay, formula of moment, remember, moment Fr sinus alpha or Fd. Okay, to calculate moment. Solve static equilibrium problems involving a combination of point forces, distributed force, moments, and support reactions. Okay, equilibrium, the sum of the force equals to 0, or the sum of the moment equals to 0. Okay, that means that the point, the material is in equilibrium, static equilibrium. It might not be equilibrium in terms of dynamic, okay, energy. Okay, the energy might change, okay, but in terms of static, okay, the observable force, okay, it is in equilibrium. Okay, understand the concept of moment of inertia and product of inertia. Okay, moment of inertia just now, ISX, IYY, etc. Understand the effects of force and moments on the motion and deformation of a body. So what can this force and moments cause to the motion and deformation of a body? Okay, that's why we need to calculate all the forces and moments. Okay, so thank you. So that's all. Okay, so I will upload this slide so you can take a look and try to do example that we have in the slides. And I will also give you assignment, okay, final assignment. So this assignment is actually related to a bit of the static here, the force calculation of force of a spring, etc. And then it relates also the mathematics, a bit of mathematics, because you need to calculate, to use vectors, and to know how to solve a linear algebra equations. And at the same time, you have to use computer programming. If you know Python or MATLAB, you can use Python or MATLAB to code, coding, okay, to program the equation, okay, to program the equation, and so that you can solve the problem. Okay, so I'll show you. I'll show you the. Okay, wait. I'll show you the assignment that I want you to do. Okay, yeah. Okay, not this one. Wait, this one. Can you see? Wait. Okay, again, sorry. Okay, so this is the assignment that you need to do. Okay, idealized spring mass system play an important role in mechanical and other engineering problems. Okay. Okay, so we have okay, this one. Okay, at this point, numerical methods can be applied to obtain a solution. Okay, if you have three mass here, M1, M2, and M3, with gravitational force, gravitational force 9.81. Okay, and the K, the stiffness of the spring is 10 kilogram per square seconds. Apply any method of linear algebra equations that you know to solve for the displacement using programming software. So you need to calculate the displacement x1, x2, and x3. Okay, but in order to calculate this, first you need to form the equation of the force, okay, as acting on these three masses. And once you get the equation of the force, the sum of the force as acting on these three masses, you will have kind of like a linear algebra equation. Okay, you will have three linear algebra equation because you have three mass and three displacement. Okay, you have three linear algebra equations. Okay, and then you need to calculate the displacement x. We need to find S1, S2, S3. Okay, so you will have kind of like a matrix. The linear algebra, you will have like a three linear algebra equation. So it is like a matrix 3 times 3, 3 kali 3 matrix. Okay, so you solve the matrix, and you will find the S1, S2, S3. So in order to solve that, to solve the linear algebra or the matrix, you need to program the software. I want you to program the software. Okay, not calculate by hand. Okay, so program the software so that you can get the answer of the S1, S2, S3. Okay, so the instruction here. Okay, the instruction here I will edit so you can you need to submit. Okay, you need to submit so the assignment, sorry, you need wait, okay, so you need to submit wait, okay, so you need to submit your programming code, okay, with record less than 10 seconds video of the program running to show that you have program you have code the program, okay, the calculation, and email your coding and video to me. Okay, I will change the deadline, so I will give you deadline until 12 28th June. So you have 3 weeks to finish this assignment. Or 30, I'll get until 1st July lah. 1st July, okay? 1st July, you have 3 weeks to finish the assignment. Okay, so please do this. Okay, if you have any questions, any problem, you can direct to me. Okay. Okay, so that's all. So and that will be all for our this class, for this course. So you won't have exam for this course. So you just need to do your assignment. The first assignment you already done. Okay, thank you. Okay, and this will be your second and last assignment, and then that's all for this course. Okay, so I hope that you at least learn something from this course, and something to refresh, okay, your fundamental knowledge on mathematics, static dynamic, and also a bit of programming. Okay, okay. Till then, thank you very much. Assalamualaikum.